Hey guys, let's look at this 111 minimum depth of binary tree. It's easy. Give it a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Given a binary tree like this, the return its minimum depth is 2. Number of nodes along the shortest path from the root node down to the nearest leaf node. What does it mean? So we have to value. So this value is the shortest, right? So this is 2. I think so. So let's do it. This must be DFS, depth first search, I think. Once we find one, every time we found a leaf node, we calculated the path, if it is shortest or not. And then if it is shortest, we update the node. Okay, let mean distance equals number infinite. There is infinite, right? Number infinite. Positive infinite. Okay. Positive infinite. Positive infinite. Alright. Oh, wait. Positive infinity. Infinity. Shit. God. Okay. Let depths, mean depths. Depth is 0. So we will sum up. We will use DFS to sum up the distance, and once we met the leaf, we update it. How we should do the DFS? We'll use recursion, right? If we use recursion, is it okay? Let's create a walker. Walk. Yeah. How can we update the mean distance? Walk. Okay. Let's say we const a walk. Node total distance. const distance past distance if node, okay, distance is past node plus node val. If node left or if node left, then we will walk. If node left is null and right is null, then we say we made leaf node, and then we will just if distance is if the distance is smaller than mean distance equals distance mean depth past depth. Equals past depth. If node left, walk node left. Past distance is distance past depth plus 1. If node right, walk node right distance past depth plus 1. This we can walk, so we will walk routes past distance 1. Oh no, it's 0. Past the depth is 1. And then we return mean distance. Run the code. We're wrong. Output is 12. Mean depth. Shit. Sorry. Oh yay! It seems that we're getting right. Runtime error. Cannot read properly a val of null. God. What? What is that? Input is empty, so if root is null, return mean depth. The edge cases. Oh, it seems I'm wrong about this one. Okay, so -8, 7, 6, null, 7, null, 6, -8, -7, 7, 6, null, 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 5. 2, right? Okay, so we traverse I'm not sure. I'm not sure what does it mean is shortest path. So if the tree there is a number, what does it mean? We don't check the sound. We don't check the what's the number. What does the number mean? If that's the case, we don't think. If that's the case, we don't check this one. If pass means this, it's like this. We don't pass in distance. Just pass 1. Really? Hmm? 3, 9, 20. 3, 6, that's 2. Huh? Why 0? Let's run the code. Got 0. Ah, God. Here, I made a mistake. It should be number positive infinity. Hmm? Then what's the meaning of this wait? Recursion. Yeah, recursion. DFS strategy. Left null, return 1. Main math main. Complexity. We visit each node. We revisit here, and then we walk. So each node exact once. Actually, there will be no call stack, so we are creating a walker. DFS iteration. Why we create a stack? Yeah, cool. Actually, this we're using a walker. Actually, yes. Yeah, even we write this walker, it would be also recursion. It's not very good. Especially because every time we yeah, because we use recursion, it will be a stack, keeping the call stack. We need to rewrite it to DFS iteration. So let's try rewrite it into DFS iteration. So DFS iteration is very DFS is yes, it's very simple. I think the DFS is just using the stack and for BFS we will just use a queue. Yeah. The solution says also if you use this one, DFS, yeah. Okay, let's rewrite into DFS iteration. It's very important that I think they will be highly possible that this problem is being asked in the interview. So the mean depth, I think it could be kept the same. This could be also kept the same. So let's current stack. We use an array to say to be as a stack. The first thing is should be root should be in it, and then while the current stack is not empty, we pop const node equals current stack pop. So when we pop this, I have to keep track of the depth. That is a not cool. How can I track the depth if I use DFS? We can use the depth stack. You can also use a depth stack equals 0, 1. So the pop const depth equals depth stack pop. If node left and node right are both empty, we say then this is a leaf. This is a leaf. Then if depth is smaller than mean depths equals depths. If the node left, we first push the right push the right one, and the current stack push node depth stack push depth plus 1. Also, we do the same to left. Dot right, node dot left, and finally we return mean depth, and it should be solving the problem. Current stack's not defined. Current stack. Oh shit. Let's submit. But actually it's not fast. I don't know why. We use 2 stacks, so that is not optimal. Let's say this is here. It is the linked list. Huh. If we don't use 2 array, we maybe just push into the number together, which is a 1. So we can use depth node and depth like this, pop for once, and the depth node, yeah, and then we should push node right, depth plus 1. Left, right, depth plus 1. Will be faster? Faster, but not fast enough. Anyway, this is just the practice of our transformation from recursion to iteration. The next one we just try use BFS. Okay, the BFS will use a queue, but we use a queue, and we use a queue. It's also like this. We just push the first init. One thing is that we don't pop and we don't use stack, because we use first in first out, so that we can always traverse all the parent node in the same level. So node depth this is not pop, but shift. We get to the first node and then check if it is right. If this and we can break. Just return mean depths. Return depths. We don't need to keep track of the mean depth, right? Yeah. We can find the first one. Just return the depth. Okay, so if the node left there is, we push the node left and depth, and right we push right depth, and then finally, oh, we only there always will be a return. So we run the code. Current stat. There's no current stat. Sorry. It is Q. 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 Still not that fast. Anyway, let's take a look at all these methods time and space complexity. The first one is it said it's recursion. Recursion. Yeah, recursion. We actually did use recursion as the first approach. Time complexity actually for case there's n nodes. N nodes. The recursion for we just actually traverse on each node for only one time, so it should be O n space. Time is on space. We keep track of the call stack, which is the depth. Actually, the averagely, I think it should be log n, right? Worst case is on, yeah. Worst is on. DFS iteration time. Also, it's on because for each node we only traverse once. A space, we use a stack. The maximum stack will be also the same. So actually, the space will also be O. Averagely should be log n. Worst on. Time complexity on, yeah. Worst case n. Yeah, but for BFS iteration time, so these I don't know. So these averagely, I think if we think that it might be n fast and in the well, so you should think O log n. No, averagely I think we can n minus 2 divided by 2, half of them. So the time complexity is the same. Space. So we use a Q to keep track every level. So averagely, worst case, it will keep O worst. It should be O and ON. Space is also ON. Actually, I think for worst case, it should be the longest one. So the space would keep to 2n. Averagely, averagely, I think if it is a complete tree, but if averagely, I don't know. In the worst case, for a balanced tree, we need to visit all nodes level by level up to the tree height. That includes the bottom level only. This way, we visit, time complexity is on. Space complexity, it's the same. I think it would be yeah, 4. Okay, so that's the end for these 111. Thanks for listening. Hope to see you soon.